Hello, a very warm welcome to everyone here and those who are joining us via Zoom webinar. Thank you for joining us for this chemistry masterclass. Now, before we begin, there are some housekeeping announcements. First, please adhere to the safe management measures. Maintain a safe distance of 1 meter apart, sit in the designated seats here in the LT, and please keep your masks on throughout. In the event of an emergency, please follow the directions of the ushers and evacuate in an orderly manner. We also kindly remind everyone to please put your phone to silent mode. At the end of the masterclass, please exit the lecture theatre using the door on the right of the screen. There will be a Q&A session at the end of the masterclass, but feel free to send in your questions via the QR code, which you can see here on screen, or visit pollev.com/Q&A-LT27. That is pollev.com/Q&A-LT27. And for those of us who are joining via the webinar, in the event that the Zoom session ends or disconnects unexpectedly, please rejoin us at the same link. Today's masterclass is conducted by Associate Professor Adrian from the Department of Chemistry. He will bring us through some chemistry which science thought was impossible. And it all started from the innocent question of how did the tiger get its stripes? He will delve into the field of modern nonlinear chemical dynamics and the connections it shares with the dynamics of natural populations of predators and prey, as well as the cyclical behavior of unemployment and wages. Let's welcome Prof. Adrian.
Hi, everybody. We'll just get the technical stuff organized. So thanks, everybody, for coming. Hopefully, we're going to have a fun session. We've got a few experiments, as you can see, set up. I'm going to be rather ably assisted by Erwan Iskandar, who's going to be really helping with the chemical demonstrations. I am a theoretical chemist, which means I don't do experiments as much as possible. I think as an undergraduate, I held the record at my university for the most visits to hospital, not a record that I'm particularly proud of, but it did tell me that experimentation really wasn't my thing. So as I said, many thanks for coming to this masterclass talk. I am, as was just mentioned, Associate Professor at the Department of Chemistry here at the National University of Singapore. And the title of my talk, as you will have realized, is How Did the Tiger Get Its Stripes? So you may wonder, actually I'll take this off, I don't need to wear this. Hopefully that'll be a little less muffled. You may wonder why a chemist really has tasked himself with trying to answer such a question. It is a question, I think, that has fascinated me since I was a boy, quite frankly. I was brought up on the Just So stories of Rudyard Kipling, and this question was the basis for one of his pourquoi tales. That said, it is also a question that has really rather excited many storytellers over the years, and has woven its delight really into the mythologies of many cultures. One of my favorites is a story that comes from Vietnam. In its telling, Tiger is described as the proudest of all the jungle animals. Tiger was most proud of his beautiful golden coat. But Tiger did not possess wisdom and was jealous that only man seemed to possess it. Approaching man, Tiger demanded that man gave Tiger its wisdom. Man, realizing the danger, used his wisdom to convince Tiger to allow man to tie Tiger to a tree with a rope. While trying to escape, Tiger burnt his coat on the rope, leaving permanent stripes on his golden coat. The other animals laughed at Tiger, who skulked away into the jungle shadows to bemoan the loss of his beautiful golden coat. Man had given Tiger a modicum of wisdom, but perhaps not in the way that Tiger intended. A wonderful story, I think, that teaches the values of courage and resourcefulness, that you have to earn wisdom through experience. But what does science have to say? Biologists argue that tigers evolved stripes over generations. Modern tigers' ancestors with stripes would have been selected for because they would have more easily blended into their surroundings, making them more successful hunters. But why would they have blended more easily into their surroundings? Surely the tiger's markings would, especially their beautiful golden coat, would make them really quite visible. Well, they're certainly very visible to us, I would imagine, but their preferred prey, which are deer and other hooved animals, have limited vision. Unlike ourselves, who have trichromatic color vision, we have retinal cells in our eyes that can distinguish red, blue, and green. Their prey really only have dichromatic color vision. Absent are the cells that distinguish red. What this means is this is what the deer sees. Okay, you can see that the tiger's golden coat appears green to their prey. And the vertical stripes in this instance now are helping the tiger blend into its surroundings. This is an example of disruptive coloration. They help to break up the tiger's shape and size to more easily blend in with trees and tall grasses. The biologist's explanation explains why tigers have stripes, but I'm not a biologist. And my question is not why do tigers have stripes, but how do tigers have stripes? The biologist can answer the why question. It's up to the chemist really to answer the how question. The answer to the how question is to be found in the laboratories of the Ministry of Health of the old Soviet Union. In 1951, a chemist by the name of Boris Belousov, working in that laboratory, chanced upon the discovery of an oscillating chemical reaction. This oscillating chemical reaction was so profoundly out of the orthodox that Belousov could not get his findings published, despite having photographic evidence. The editors at the time simply did not believe him. They were totally incredulous of his work and claimed that the phenomenon that he was describing was impossible. In fact, the only contemporaneous documentation of his discovery is a brief mention in the proceedings of a conference. Why did the editors not believe Belousov? Well, let's consider the most studied reaction in all of chemistry. And I just want to pause for a moment. Can anyone guess what that reaction might be? It's certainly a reaction that you would have studied at school. Does anyone have an idea? What is the most studied reaction in all of chemistry? Just shout out. What's your favorite reaction then? Well, it's a bit of a trick question. The most studied reaction in all of chemistry is this one. Chemical A reacts to form chemical B. It's really the basis. It's really where everything starts. It's how we learn really about how chemistry works. That said, I think it's still a fascinating little reaction. If we assume that it takes place in a single step, that it's an elementary reaction, then we can predict how A is going to change with time. Okay? So how does this reaction proceed? Well, this is what happens, as I'm sure we're all familiar. Chemical A monotonically, so smoothly changes over time, doesn't jump around, monotonically and exponentially decays with time. This is what we expect. Interestingly, or at least I believe interestingly, the mathematics behind this decay also explains many other things. It explains, for instance, why air pressure decays exponentially with height. It also explains why the height of the froth on your pint of beer decays exponentially with time. That latter discovery is a real published scientific paper. This was published in 2002. It won the infamous Ig Nobel Award a couple of years later. Exponential decay, as I'm sure you'll realize, is a very common feature in nature. At the time of Belousov, it was believed that all chemical reactions will show a monotonic change over time, that any chemical system moves steadily towards equilibrium. Right, okay. I think it's time to have a little bit of fun, and I'm going to have to get dressed up for this. What I want to do is show an oscillating chemical reaction. And I have to say, initially, this is not the oscillating chemical reaction that was discovered by Belousov. We will come to that later. Iskander's going to show that. Sorry, Erwin, you're going to show that on the visualizer in just a moment. But we're going to look at a different reaction. This one was discovered by Thomas Briggs and William Rauscher. What's interesting about this one is Briggs and Rauscher, they weren't academics studying in a university researching these things. They were two teachers in a high school in California when they made this discovery. So, okay, let's have a play with this. Let me get dressed first of all. Right, just let me get dressed. So what we've got here are three colorless liquids that Erwin has labeled A, B, and C, so I don't forget the order in which I meant to add them. So we have, this is hydrogen peroxide, is about 4 molar solution. We've also got some potassium iodate that's been acidified with sulfuric acid. And then finally, we've got a starch solution that also contains some manganese sulfate, as well as malonic acid. These are allegedly large gloves. Right, so what I'm going to do to start this reaction off is I'm going to mix the hydrogen peroxide with the potassium iodate that's been acidified. And what that will do is release some of the free iodine. Okay, so I'm expecting that if I leave this for a little while, it's going to go a kind of yellow color. I don't want to go to the hospital. Okay, I'll do. This is what we call bucket chemistry. It's the kind of chemistry that hopefully doesn't go wrong, at least not in my hands. So you might just be able to detect now that it's going a slight yellowish tinge. Let's turn it down a little bit. I'll speed that up in a little moment. So now I'm going to add the final solution, which has the starch solution, as well as the malonic acid and the manganese sulfate. Okay, hopefully now you can definitely see it's gone yellow. And let's see what happens. Nothing too surprising so far. So we've seen a few cycles there. This is what we mean by an oscillating chemical reaction, that it goes through this transition from the yellow solution through a transparent phase and then to the dark blue, and then it returns to the yellow, and then the cycle repeats and repeats and repeats. And if we're lucky, this may repeat up to about 40 times over the course of several minutes. It is, quite frankly, the closest I think chemistry comes to real magic. It is, in fact, an experiment I sometimes show in a kind of magic show, because it is so wonderful and so really quite strange and exciting. So what is happening, though, with that experiment? Let me take these gloves off before I start touching anything I shouldn't. Why didn't the editors believe Belousov when he wrote about such a system? Well, the problem is that this phenomenon seems to suggest that in our reaction of A to B, that when A has run out, the B that was formed reacts to reform A to start the process over again. That seems to sort of break several laws of nature, not least the second law of thermodynamics. That's not a law you can break. Fundamentally, where is the free energy coming from to convert the B back to A? That's why it doesn't make sense. And that's why the editors at the time were skeptical and didn't believe Belousov. So how can we understand what is going on here? And indeed understand where the free energy is coming from in order to drive this reaction? Is there a physical analogy that can help explain things? Right, okay, so what I want to do now is introduce these ramp walkers. Okay, so this is just made out of a piece of cardboard. The sellotape is on there, there's no springs attached. You can come down and have a look at these later. And we watch what happens when I put this ramp walker on this ramp. Okay, so if I pop it up here, let's see what happens. It slowly, as its name suggests, walks down the ramp. What is driving this behavior? Well, in this particular case, of course, it's going to be gravity. If you look closely, you'll also see that it is walking down this ramp. It's not sliding down this ramp, it's walking down this ramp. It moves from its right foot to its left foot and back again and so on. Okay, so we've got a variety of different ramp walkers down here. And in fact, I was introduced to ramp walkers by a science teacher by the name of Bruce Yeaney, who has got some wonderful experiments that he shows on YouTube. So if you do want to have some fun later, look up his channel and have a look at some of the experiments that he has. And this is one of them. So my question to everybody at the moment is, if I take these two ramp walkers here, then which of these two is going to get down to the bottom of the ramp first? The big one or the little one? Hands up if you think the big one gets to the bottom first. Is that just one person? Hands up who says the little one will get down to the bottom first. Okay, let's see who's right. I'll start them off at the top and let's see what happens. Ready? Ooh. I'm not hopeful that the big one is going to get there first. To be fair, the small one's cheating. The small one's sliding every other few steps. Don't judge a book by its cover. Just because you're small doesn't mean that you're not going to be the one to perform. Oh dear. Big ramp walker gave up. So that's what we have. Let's have a look at a quick video to zoom in and see what was going on there. So when we slow the process down, you can see what's going on as the walker moves from its right foot to its left foot and comes down the slope. The driving force for this is still gravity. That oscillation from right foot to left foot, which is the analog of what's going on chemically in our Briggs-Rauscher reaction, that driving force is gravity. Now, returning, I suppose, to the Briggs-Rauscher reaction, the precise chemistry behind it is rather complex. We will look at the chemistry of one of these oscillating chemical reactions in detail later. But for the Briggs-Rauscher reaction, it essentially involves two key processes. The slow consumption of free iodine by the malonic acid substrate, and that's in the presence of the iodate, and then a fast autocatalysis process involving manganese and some of the free radical intermediates, which convert the hydrogen peroxide and iodate to free iodine and oxygen. Quite frankly, however, knowing that doesn't really help us to identify any chemical oscillations. Why do those reactions lead to chemical oscillations? Well, instead, let me write down a set of chemical reactions which might explain things. The first reaction is between A and X to form 2X, okay? The second, well, first of all, notice that this is one of those autocatalytic processes I just mentioned, okay? That this reaction of X produces increasing concentrations of X. That's why we call it autocatalytic. The second reaction is between X and Y to produce 2Y, and the final reaction is Y to produce B. Again, I think we might struggle to see why that leads to an oscillating process. What we're going to do is think of these reactions ecologically. So we're going to replace A with grass, X with rabbits, Y with wolves, and B with dead wolves. A little bit dark, but such is the cycle of life. So what's going on here? The first reaction is saying that rabbits eat grass and produce more rabbits. And so what will happen is that the population of rabbits will increase rapidly. The second reaction, okay, because of the increased rabbit population, the second reaction starts to speed up. And the second reaction says that the wolf eats the rabbits and produces more wolves. And so the wolf population is going to increase and the rabbit population will drop. Now, as the rabbit population drops and what we'll see is that the wolf population will begin to die off in that final reaction. And the wolf population drops. And this is going to allow the rabbit population to recover and increase and start the process all over again. And so we get that kind of oscillation. What we should notice is that that kind of oscillatory behavior requires grass to be present at all times. If we remove the grass from this system, the rabbits will die. And if the rabbits die, the wolves will die, will stop reproducing, and ultimately the wolves will die off. And what we'll be left with is dead wolves. And this is essentially what will happen in our oscillating chemical reaction. You notice the oscillations have stopped. I'm left with my bluish solution at the end. The overall reaction of grass leading to dead wolves is the driving force for this entire process. It drives the oscillating system, and it's providing the free energy necessary for the system to progress. So the mathematics behind this were discovered by Alfred Lotka and Vito Volterra. Whoops. And it looks like this. So what I've written down here are two rate equations. So the first one tells me the rate with which rabbits are changing with time. So I've got a process here related to the rabbit birth rate and the process related to the rabbit death rate. The rabbit birth rate, okay, just depends on how much grass is present. The death rate depends on how many wolves are present. Why? Notice there is no ecological process in which the rabbits die of old age. The second process describes how Y is changing with time. Okay, their population increases depending on the population of rabbits, and then they die off in a steady process. What does that look like if I integrate those two equations with appropriate birth and death rates for wolves and rabbits? Well, it looks like this. We get that oscillatory behavior. And you can see exactly how I was describing it. As the rabbits eat the grass, their population increases. But as their population increases, the wolves' population increases. And eventually, the rabbit population decreases, and so the wolf population will also die off, and we return, allowing the rabbit population to recover and the rabbit population increasing once more. Great. So what is going on chemically? Let's look at this in a little bit more detail and see whether we can understand it in some detail. We can, I think, first of all, recognize that these kind of reactions, for instance, they don't just explain things like the chemical reactions I've shown here, and also the kind of predator-prey cycles that I've described. They also, in fact, have a long history in use in economic theory to explain cycles and economic activity. And indeed, this ecological analogy that I've just introduced isn't just a thought experiment to explain my chemical reaction. It was also witnessed in nature. These are the records from the Hudson's Bay Company, their first sales, and they reveal a similar oscillations in the populations, in this case of snowshoe hares and Canada lynxes over several decades. Again, fascinating, but I seem to have strayed away from my question of how tigers get their stripes. Let's return to the work of Belousov and look at the reaction that he developed that was subsequently refined by Belousov-Zhabotinsky. A reaction now referred to as the Belousov-Zhabotinsky reaction. This reaction is far more temperamental, and I think we've had a little bit of a trouble there, haven't we? It hasn't come off, so instead I'm going to have to show you a video of what it looks like. What you can see here are these blue rings appearing in this Petri dish. Okay, this has been speeded up by about a factor of 8, I think. So you can see initially these little blue dots appearing in this reddish, in that reddish solution. And then the blue rings growing to form further rings. And then inside those rings, more blue dots appearing and growing. And so the pattern continues, producing these kind of really wonderful structures. The positions of the blue dots is entirely random. There's imperfections in the original reddish solution, which kind of break the symmetry and allow the process to start. Unlike the Briggs-Rauscher reaction, which evolved temporally, this one's evolving both in space and time. And it's this spatial oscillation, I think, that is suggestive of the answer to the tiger stripes question. Can we understand what's going on chemically, though? Do we understand what's happening? We can go into a lot more detail, but I know that I'm running out of a bit of time. I was going to scare you a great deal with the chemistry that's underpinning this, that we would in class go through in a great deal of detail to explain what's going on. But again, we get a cycle that involves the removal of bromide ions, the autocatalysis reaction of bromous acid, and the oxidation of iron 2 to iron 3, and then the reduction of the iron 3 back to iron 2, and the production of bromide ions to start the process all over again. Writing rate equations, we can use those rate equations to solve them numerically and reproduce what we saw in that video. This same kind of periodic process. When the bromide ion dropping below a critical concentration, the bromous acid catalysis kicks in, and we get the reduction of iron 3 back to iron 2, and we get the oscillatory behavior that we've just witnessed. So Belousov was right. But is this the origin of tiger stripes? The first to suggest that the origin of tiger stripes was chemical in nature was due to perhaps one of the most influential scientists of the 20th century. And that person was Alan Turing. He is perhaps better known, not as a chemist, because he was certainly not a chemist. He was a computer scientist. His influence on computer science is unrivaled, and indeed in artificial intelligence. He was also famous for cracking the Enigma code, the Nazi Enigma code during World War II. And that was portrayed by Benedict Cumberbatch, of course, in the film The Imitation Game. Not satisfied, though, with his work that rightly holds him as the father of theoretical computer science and artificial intelligence, Alan Turing also published a paper in 1952 that would ultimately explain the origin of tiger stripes. He suggested that chemical substances called morphogens could react together and diffuse through a tissue to give rise to patterns such as the walled leaf patterns that you see, and also the stripes and spots on the big cats such as tigers and leopards. He suggested that chemical substances called morphogens could react together, diffuse through the tissues and create those kind of patterns. That was a tantalizing idea, and it didn't really get the kind of experimental confirmation until 2012, when this paper was published. Researchers found that interaction between two morphogens, the fibroblast growth factor and the sonic hedgehog protein, alternately triggered and hindered cellular activity, leading to the development of these ridged patterns that you see on the palates of developing mice. And these pictures here show what's happened if you interfere with the fibroblast growth factor and the sonic hedgehog gene. So this study provided the first experimental identification of an activator inhibitor system at work in the generation of stripes. It, I think, goes a long way to confirm that the how of tiger stripes is the oscillating chemical reaction. The work of Boris Belousov that so confounded the scientific community is now recognized as the explanation of tiger stripes, of leopard spots, of firefly flashes, and indeed of your beating heart. So despite leaving science in disgust after failing to get his important work published, he has achieved a legacy that few scientists can claim. His work ultimately led to the field of modern nonlinear chemical dynamics. What I find particularly satisfying with this story is its intrinsic interdisciplinarity. Scientists from the fields of biophysics, chemistry, ecology, mathematics, and computer science contributed to its resolution. It is in these beautiful and I think fascinating structures and in their study that we understand really the need for an interdisciplinary education and really the reason why we put together the College of Humanities and Sciences. And I hope that this story will inspire you perhaps to join us next year. And I look forward to seeing many of you next year. And I think I'll end there and I'll entertain any questions that you might have with regard to this or anything else. Many thanks, everybody.
Thank you so much, Prof. Adrian, for guiding us through this masterclass. We will now be opening the floor to questions. You may send in your questions by scanning the QR code here on screen or visit polev.com/Q&A-LT27. It appears the QR code is not on screen, so please just head over to the website link instead.
One of the big discoveries of the 20th century, perhaps the biggest discovery in molecular biology, was the cloning of Dolly the sheep. If we had cloned a tiger, do you think its tiger stripes would have looked the same? as the tiger from which it was cloned. If we cloned a tiger, do you think we would got the same kind of belief that that had actually happened? I think the chances are no, it would not have looked the same. And all our kind of preconceptions of what a cloned animal should look like would have been broken. So it's probably a good idea not to have cloned a tiger, at least if you're trying to prove that cloning was possible. Okay. So yes, so that was due to the structure in the eyes. So a deer has dichromatic, it can't see red. And so a tiger looks green to a deer. With regard to fingerprints, I think the answer is yes, but I'm not 100% sure. For that final question up there, I'm going to leave that to somebody else to answer. We've got people from chemistry, haven't we? So what's happening with regard to the time and space things is that there's this coupling between the rate of the reaction itself and the rate with which the structures are diffusing. So when you get the nice balance between diffusion and reaction kinetics, that's when those patterns start appearing. So they have to be at the right ratio, as it were, to see those kind of patterns that we saw. No, it gets stopped. I think the patterns develop during the embryonic stage, but you can imagine that it gets quenched before birth. So it's fixed in place after, well before birth actually happens. Well, I think with regard to this one, it was more the fact that this little ramp walker cheats a little bit. It slides, so it gets down a bit faster. So we need a rougher surface, really. But it's interesting. It'd be interesting to sort of study why, whether the length of the legs was important, whether the curvature of the feet was important in determining how fast it can get down, how springy the bend has to be to support the rocking motion and it coming down the slope appropriately. Starch solution is just starch. The second solution was a mixture of both starch solution, manganese sulfate, and what else do we have in that one? Oh, the malonic acid as well. But the blue color here is the complex between iodine and starch. Very famously, it has that really bright blue color. You can do chemistry both as a major on its own or as a minor. Most fascinating thing in chemistry, other than oscillating chemical reactions? I think that, what fascinates me as a theoretical chemist really is that is how mathematics describes chemistry. I touched a little bit on that, showing you some of the simulations I put together in order to reproduce what we were observing. What I really find most fascinating, though, is how quantum mechanics manages to really describe what's going on at a fundamental level. That it's only in quantum mechanics that you get a true picture of how atoms and molecules come together to bond. I know that's a little bit abstract, but that's what really gets me going. So the reason why B got back to A was because originally I showed you a single-step process, A reacting to form B. When I created a mechanism, the overall reaction was A to B. But the steps in between are what allows you to oscillate, the intermediates oscillate as A gets converted to B. But the A getting converted to B is providing the energy for those oscillations to take place. So you're not seeing A or B in here, you're seeing the intermediates in the mechanism between A getting to B. And it's those intermediates which can oscillate. So, how many chemistry classes do you take? And practical classes? I'm trying to remember, the curriculum has just changed. Please update me. One laboratory class per week on average. Okay, that seems to make sense. Possible careers? I always love this question. So I come from the UK. My Prime Minister was a chemist, Margaret Thatcher. She was a chemist. So clearly, becoming leader of your country is, getting a chemistry degree is important in that. What else can you do? I had friends that went into the financial markets. Being able to model some of those chemical reactions, being able to do that kind of analysis, really important in financial markets. So it can lead to careers in the financial markets. What else? I've had people go into teaching, of course. That's what I did. Yeah, I think what I see as being most important about university education is not that you should feel restricted in what you want to do in the future. Although you might specialize, although we're trying to ameliorate that as much as possible, you might specialize in one particular subject. Your major may well be chemistry, but your horizon has been broadened because of that university education. Understanding things like this needs perspectives from different areas. It required a computer scientist to tell us that, to use his knowledge and his computing skills to be able to sort of say, well, look, these stripes might well be sort of chemical in nature. He didn't understand the chemistry, but he could run the computer models necessary to explain it. And recognizing that the mathematics explains so many other things, economic cycles, and as well as sort of predator-prey cycles and so on, is also recognizing, so how important it is to bring different subjects together. Being inspired by the story to begin with is also important, I think. Compulsory core maths. Do we have compulsory core maths? No more compulsory core maths.
Unfortunately, I think we need to stop the Q&A here. But thank you all so much for your curiosity, and thank you, Prof. Adrian, for answering our participants' questions. Should you have any other questions, you may send us an email at the email address shown here on screen. Certain questions we may be unable to answer, for example, some of the curriculum structures which may be changing, but do not hesitate to visit the websites and head over to the emails stated on their websites as well. You can also send your queries there. So we have now reached the end of our masterclass on how did the tiger get its stripes. We hope that you have been able to learn more about this course and enjoy your glimpse into learning at today's experience NUS Open House. There are many activities that have been planned for today around the campus, such as student life activities happening at UTown. We wish you a good day ahead, and please exit the lecture theatre via the door here on my left. Thank you.